Welcome to the podcast series of Crispy Info. In this podcast, we will talk about quantum computing, the significant milestones in quantum computing, the present limitations of quantum computing, and India's commitment regarding National Quantum Mission 2023. We will also talk about the road ahead. So, let's start this podcast. The topic of the podcast is a beginner's guide to quantum computing. Starting from the context, quantum computing, rooted in quantum mechanics, promises to solve complex problems beyond the reach of classical computers. Proposed by Richard Feynman in 1982 to simulate quantum systems, it emerged as a solution to classical computers' limitation. Since then, progress includes the development of qubits using superposition and entanglement, improved error correction, and a scalable hardware, paving the way for applications in cryptography, optimizations, and drug discovery. Quantum computing. So, we will understand classical computing first, and then we will be understanding about the quantum computing. Classical computers operate based on principle of classical physics. The basic unit of information is the bit, which can be either 0 or 1. All types of information can be represented using combinations of 0 and 1 in the binary system. In quantum computing, qubits is the fundamental unit, not the bits, because bit is the fundamental unit of classical computing. Quantum computers rely on quantum bits or qubits for computations. Qubits can represent 0, 1, or a state that is partly 0 and partly 1 simultaneously. This ability to exist in multiple states is unique to qubits and enables quantum computations. Now, the key principles involved in quantum computing are superposition and entanglement. So, superposition is a key quantum principle. Qubits can exist in a state of superposition, holding both 0 and 1 at the same time. Example: a spinning coin that represents both heads and tails simultaneously until it collapses to one state when observed. Superposition allows quantum computers to perform multiple computations at once. The second key principle involved with the quantum computing is entanglement. Qubits can be entangled, meaning their states are intrinsically linked even if they are far apart. Measuring one qubit instantly provides information about the other regardless of distance. For example, if a pair of gloves are kept in separate boxes, opening one reveals the other's state instantly. Entanglement enables faster information processing through shared states. Now we will see the advantages of quantum principles. Superposition allows quantum computers to process exponentially more data than classical computers. Entanglement facilitates simultaneous information sharing, speeding up computations. These principles, rooted in quantum mechanics, unlock the immense potential of quantum computing beyond the scope of classical physics. Now we will see the significant milestones in quantum computing. Quantum computers versus classical computers. Quantum computers are technologically advanced but may not always outperform classical computers in every task. Specific tasks have been developed to demonstrate the unique capabilities of quantum computing. Shor's algorithm, revolutionizing the factorization 1994. So created by Peter Shor, this algorithm can factorize large number in moments compared to millions of years required by classical computers. Major implication for data security, as it can quickly solve problems like larger number factorization which are used to secure encrypted data. IBM's Q System 1, the first commercial quantum computer in 2019. IBM introduced Q System 1, the world's first circuit based commercial quantum computer. Circuit based designs with quantum gates are versatile and suited for general quantum computing applications. Then, Google's Sycamore processor, achieving quantum supremacy in 2019. Google's 53 qubit Sycamore processor solved a problem in 200 seconds that would take a supercomputer 10,000 years. This milestone marked quantum supremacy while quantum computers outperform classical counterparts for specific tasks. Google's Willow quantum chip, scaling with error correction 2024. Google unveiled Willow, the first quantum processor with error corrected qubits that improve as they scale. Quantum error correction is critical to maintaining quantum states long enough for meaningful calculations. Willow completed a standard test in 5 minutes, a task that would take the best supercomputers 10 trillion years. Progress and potential. So, these milestones illustrate the rapid advancement of quantum computing, showcasing its potential to solve complex problems far beyond the reach of classical systems. Now, we will see the present limitations of quantum computing. So, it has high cost and complexity. Building quantum computers is extremely expensive and technically complex. Maintaining the stability of qubits is challenging due to high error rates and issues like decoherence caused by environmental noise. There is a need for large scale quantum systems. Current quantum computers have limited qubits but solving major problems, for example, drug discovery, astronomical research, they requires millions of qubits. Scaling quantum systems to such levels remain a significant hurdle. Now we will talk about the National Quantum Mission, India's commitment in 2023. Recognizing the potential of quantum computing, India launched the National Quantum Mission. The government allocated 6,000 rupees crore over 8 years to advance quantum technology and develop quantum computers. Now, what are the road ahead? While the challenges are substantial, the advancements and investments highlight the clear potential and promise of quantum computing. Thanks for listening to the podcast. Please subscribe the channel and share with your friends.